Hello there, stats fans. So our little statistical journey continues today. We're on to a new chapter. It's called representations of data. We've been representing data in lots of different ways. We've been looking at how spread out data is, and today's just a continuation of that really. We're looking at those bits of data that are so far out that we maybe need to discount them, and they're called outliers. To do that, we're going to start thinking about a kind of diagram that you may remember from your GCSE days, the box and whisker diagram. So on a box and whisker diagram, we've got a few different things going on. We've got our smallest value, we've got our biggest value up the other end. In the middle, we've got the median, the value that if we were to put them all in order, the one that would come right in the middle. And that'll be somewhere in the middle of the interquartile range. Q1 comes there, Q3, the upper quartile, goes there, and in between here, in the interquartile area, what that is our most typical half. That's often the data we're most interested in. That's like the range of what stuff it could be considered the average, I suppose you could think of it as. Now, how do we define what an outlier is? Well, there's different ways, and one way, they quite often like to talk about a certain number of interquartile ranges away. Now, most box and whisker diagrams, once you've added the interquartile range on once, you've probably reached your biggest value. So quite a common one is to use 1.5 interquartile ranges. So if that's that distance there, 1 plus a half would be about, that would be about 1.5 times whatever the interquartile range size was. So any data that ended up there, any data points there, would be considered outliers. Now if I was to go that far the other way, we have no smallest value outliers. That's the sort of thing we're thinking about. Now it's not only the interquartile range that can be used. You may have noticed our old friend standard deviation up at the top there, and we can talk about numbers of standard deviation. We're going to go through some examples of both today, folks. Right, so here's our first example. It kicks off with a nice bit of practice for finding quartiles. So it's a little while since we've done this. So if you remember, we've got this new technique now where we just say how many people we've got, or how many bits of data we've got, divide it by 4. Because that says 7.5, that means we pick the next one up, so we pick the 8th. So the lower quartile is going to be 1, 2, 3, 4, 5, 6, 7, 8. So Q1 equals 3.2, and then for Q3 it's going to be 3/4 of 30, which will be 3 times 7.5, which is 22.5. So we want the 23rd. So that's 15, 16, 17, 18, 19, 20, 21, 22, 23. And always check that the data has been put in order for you. Easy mistake to make. So Q3 is going to be 4.0. Strictly speaking, we should put our units in here, mmol per litre, whatever an mmol per litre is. Important if you need to know your blood glucose, I guess. Right, so there's the quartiles. Then to find any outliers, the first thing we need is the interquartile range. So Q3 take Q1, 4 take 3.2, the IQR is going to equal 0.8, and we want that times 1.5. So 1.5 times 0.8 is 1.2. So that means it's got to be that much above the upper quartile or below the lower quartile before it becomes an outlier. So 4.0 plus 1.2 is 5.2. So 5.2 is here. So everything is okay there. And if I do the lower quartile, which is 3.2, and take 1.5 interquartile ranges away, I get down to 2.0. Now 2.0 is just there. So that means that that chappie there, 1.7, is an outlier. Next up, from our blood glucose levels, we go to the exciting area of giant African land snails. So a bit of practice calculating the mean and standard deviation. They've told us what they all add up to. We could do that just by adding them up as well if we needed to. So the mean is going to be 252 divided by 12, which is exactly 21 centimetres. And then the standard deviation, we're going to need to use the sum of everything squared, they've told us, divided by how many we've got, take away the mean squared. So all that's going to mean is, I'll do that down here, we're going to have the square root of 5468 divided by how many snails? 12. Take away our mean squared, whack that into the calculator and round it to 3 significant figures, and you should have 3.3 centimetres. Sorry, 3.83. Right, so if an outlier is defined by standard deviations, plus or minus 2 standard deviations from the mean, the first thing we need to do is say, right, well, 2 standard deviations are going to be 3.83 times 2, which is 7 point something. Actually, in my calculator, I've just got it down as 4 root 33.3 because I've kept my answer exact from there. Now, if I add that to 21, I get, what do I get? I get 28.7 centimetres. And if I take 4 root 33 over 3 from it, I get 13.3 centimetres. So those are the 2 critical parts. Have we got any outliers? Not down below, 17 is well within, but up above, 28.7 would come about there. So 32 centimetres, that massive land snail, is the outlier. And they nearly always do that in the questions, to be honest, folks. At one end of the scale, there won't be one. At the other end, there will. Okay, time for a bit of practice. Pause the video and have a go at this one. Right, well, you've got 3 different ones we want to find out whether or not they're outliers. Let's just find out where our region is first of all. They've told us the upper quartile and the lower quartile. So 68 take 46 is 22. So 1.5 times 22 is 33. So at the upper end, we're looking at Q3 equals 68, add 33 is 101 centimetres. Well, I don't know if it's centimetres, doesn't say, does it? And Q1 is going to be that much smaller than the lower quartile. So 33 away from that gives us just 13. So 7 is less, so outlier. 88 is less than 101. It's within that zone from 13 to 101. They are all safe. It's anything outside, so not. And yes, 105 is too much. That is an outlier. One more question to go. Okay, here's the first part of it. Give it a go. So the mean should just be 92 is what they all add up to. We've got 9 people, 92 divided by 9, which is 10.2 recurring years. And the standard deviation, once again, we're doing just what we did before. So we've got 1428 divided by how many, which is 9. Take away the 10.2 recurring. Well, best just to put that as a fraction and square it in your calculator. And if you did that, you should have got 7.36 to 3 significant figures. So that would be years. And then time to move on to the next parts. In fact, I'm going to give you all of that so you can pause and give that a go. Right, so state with a region whether or not it's an outlier. Well, The method we've just learned is 2 standard deviations from the mean, and that's a pretty standard one to do. So the first thing to do is say 2 standard deviations equals 7.36 times 2, which is 14.72. If you add that to 10.2, you get 24.94, I think. So 30 is older, so you can say, yes, it is more than 2 standard deviations from the mean. Right. A reason why it could be a legitimate data value. You could say an adult supervising the party. You could just say it could be a parent. Now, given that we know all 9 people were children, it says clean the data. We've not talked about that before, but hopefully you may have been able to have a guess. What it means is, if that 30-year-old was really a child, that 30-year-old can't be a child. That number must be wrong. So what we do is we take that number out of it. 92 take 30 is 62. So we're going to say we've got 62 people and we've only got 8, because that is corrupt data. So you do 62 divided by 8, which is exactly 7.75 years for the mean. And the standard deviation, you would do similar thing. 30 squared is 900, isn't it? So if you take 900 away from the sum of the squares of our data, then that would leave you with 528 must be the square of all the data for the 8 correct ages. And then if we're taking away from that 7.75 squared, that should give you 2.44 years to 3 significant figures. And that's it for today, folks. Okay, catch you next time. Cheerio.